Okay, illustrative math, unit 4, lesson 5 is called changes over rational intervals. Okay, so our goal today is I can explain why an exponential function changes by the same factor over equal intervals, even when those intervals are not whole numbers. Okay, so let's look here. Here's a function. F of x equals 200 times 1.07 to the x. So a couple things to start, make sure that we understand. This is my initial value. This is my growth factor. A factor is something that you're multiplying by. So we'll call that our growth factor. Now, remember, it's 1 plus 0.07. So 0.07, that's my percent increase. So you start realizing here, 0 would be 200, the 0 term. If I start multiplying by 1.07, I kind of start realizing here that, you take your calculator, 200, really if I had a 0 term here, if I had 0 here, 0 would be 200. But then you times it by 1.07. And you get the 214 right here. And you kind of follow that same pattern here. You can kind of see that it's geometric. So I'm going to finish this out here. And then when you get here, you're like, oh, shoot, I can't multiply by 1.07. A lot of people divide it by 2, but that's not right. So what it ends up actually being is it's times 1.07. Since I'm only doing half an interval, it's kind of like 1.07 to the 1/2. Because if you think about it here, if I had a 5 here, it'd be times 1.07 to the 1/2. Because if I multiply 1.07 to the 1/2 times 1.07 to the 1/2, you'd add the powers, and the whole thing, if I move this down here, the whole thing from 4 to 5 would be times 1.07 to the first. Okay, so anytime you have a partial interval, it's half an interval, it's to the 1/2 power. If it's a third of an interval, it's to the 1/3 power. So here, the 4.25, I could just plug it in because I have a function. It'd be 200 times 1.07 to the 4.25, and I would get my number. And I get 266.63. If I didn't have a function, though, if I just said I start at 200 and every whole number I increase, my rate of change is 1.07, you'd kind of think of it as times 1.07. So it's like you're doing it 4 times. And then you're doing a quarter. So if I added all these powers, when I multiply, you add the powers. If the bases are the same, you get 1, 2, 3, 4.25. So that's where that comes from. All right, consider this function, h of x equals 4 to the x. For each question, be prepared to share your reasoning. By what factor does h increase when the exponent x increases by 1? 4 to the x is now going to be 4 to the x plus 1. So where does that plus 1 come from? Well, it's really like saying 4 to the x times 4 to the first. This is your factor. This is what you're multiplying by, because you add those powers when you're multiplying if they have the same base. That'll take us to the x plus 1. So this is what it's multiplying by. So the answer is 4 to the first. So I go from 4 to the x to 4 to the x plus 2, well, that's kind of like saying 4 to the x times 4 to the 2, because you'd add those powers to get the x plus 2. So the answer is it's times 4 squared. And same idea here. 4 to the x, if I'm going to increase by 0.5, well, that's like saying 4 to the x times 4 to the 0.5. You'd add those powers to get that x plus 0.5. So this is what you're multiplying by, okay? All right, a little quick review. 5 times what number equals 50? Well, most of you can do this in your head. You'll just say 10, okay? But really, remember, you could divide, okay, and get x equals 10. Same thing here. If they're weirder numbers here, like I might say, what's my growth factor? And everybody, when it's here, it's 5 times 10, you get 50. Everybody can figure out that your growth factor is 10. But when it's like weird numbers you can't do in your head, like we forget how we got the 10 here. So remember, it's just, you would just divide, okay? So I would divide, and I would get x equals 0.85. Okay, so your growth factor is 0.85, and it's actually not a growth factor because it's less than 1. It's actually going to be I would call it a decay factor, but our book always calls it a growth factor. Okay, so that takes me to this. After purchase, the value of a machine depreciates exponentially. Table shows its value as a function of years since purchase. If a spreadsheet tool is available, considering using it, we're not going to do that. We're cross that off. We're just going to do it by hand here. So I go by 1/2 here. So I chose that for the same number. So from 0 to 1, you're timesing it by 0.85. So kind of like I did in the first slide here, to go by 1/2, you're going to times it by 0.85 to the 1/2. Okay. So anytime you go up by 1/2, it's going to be 0.85. Because to go by ones, we're thinking 16,000 times whatever my growth factor is, I'll call it F, and it gets me to 1360. So, that's how I got the number. I divided here. And I said, oh, okay, my growth factor equals 0.85. But that's for one interval. So to go by 1/2, it's 0.85 to the 1/2. So I'm just going to take 16,000 times 0.85 to the 0.5 power, and I get 14,751. And then this is again increasing by 1/2. So I'm going to do this here. I'm going to times it by 0.85 to the 1/2. And I get the 12,539. I'm going to round. All right. So let's go to this question. I might have already answered it. The value of the machine in dollars is a function of time t, number of years since the machine was purchased. Find the equation defining F. Okay, so my initial value at 0 is 16,000 times my growth factor is 0.85. So we want a function of t time. So I have to use the variables they told me. So I'm going to use t. So it's f of t equals 16,000 times 0.85 t. So I found the values here from figuring out my growth factor and dividing it. I could also, once I find my function, I could plug it in. So I'm going to go ahead and do that. Whoops, 1.5. And you should get the same numbers here. You should get 14,751, and you should get 12,539. Okay. All right, observe the values in the table. By what factor did the value of the machine change? Every 1 year, say from 1 to 2. Well, that was easy. We know that is by 0.85 is what you're multiplying by, times 0.85. Every half year, well, we kind of already said that's 0.85 to the 1/2, or to the 0.5. That's what you'd multiply by. All right, suppose we know f of q, the value of the machine q years since purchase. Explain how we could use f of q to find f of q plus 0.5, the value of the machine half a year after that point. So if we know f of q, so f of q, you're just going to basically times it by 0.85 to the 0.5. So f of q, you would just times it by your growth factor, 0.85 to the 0.5 power, because you're adding on an extra half of year. So you're going to times it by your growth factor, but only to the 1/2 power, because you're not doing a full year. Okay, so whatever you got for f of q, which we would know, like let's say it's 10,000, you go up an extra half of year, kind of just like with your table. Every time you increase, like right here from 1 to 1/2, you multiply by 0.85 to the 1/2. Same thing here if you go up 1/2. So, like here, if I said if I wanted to go up an extra half a year, we'd have to take this value here and times it by 0.85 to the 1/2, or to the 0.5 power. Okay. All right. Graph shows the amount of medicine in a child's body hours after taking the medicine. The amount of medicine decays exponentially. So after a quarter hour, there are 7 milligrams left. So 1/4 is at 7. And then at 3/4, you're down to 3.5. So it looks like every half hour, because from quarter hour to 3/4 of an hour, you get multiplied in half. So think about this here. If I go a quarter of an hour, 3/4 of an hour, next one's going to be 1 1/4. And the next one's going to be 1 3/4. So if here I'm at 7, here I'm at 3.5, you're times it by half every half hour, essentially. So a half hour later here, if I times it by 1/2, I get 1.75. If I times it by 1/2 again, I get 0.875. So those would be my answers here. Okay, because you're just times it by 1/2 every time, every half hour increment. So how does the decay rate from a quarter of an hour to a half of an hour? So it's half of an interval here. So if from a quarter of an hour to 3/4 of an hour, we times it by 1/2, 1/2 of an hour, this is halfway in between there, you're going to times it by half of this interval. So it'll be 1/2 to the 1/2. My answer is quarter of an hour is half of a half hour interval. So it would be 1/2 is our growth factor to the 1/2 power. Now, if it was a third of an interval, it'd be 1/2 to the 1/3 power. Okay, a little review here. If I give you a graph that looks like this, your initial value would obviously be on the y-axis. It'd be 700. Your growth factor, well, we'd have to think here, 700 times what? I'll use F for factor. By what factor gets me to 784? So we'd have to divide divide 784 divided by 700 is 1.12. So that's your factor. That's what you multiply by every year. So how much is it increasing? It's increasing by 12% because it'd be 1 plus 0.12 to get the 1.12. So my function, your initial value, 700 times your growth factor to the x power. Okay, and that comes back from y equals initial value a times b to the x. So then to find 3.5 years, we could now just plug it into my function. Once you find your function, there we go. All right, pretty easy. Now, if I wanted to kind of do a table like I was doing here, 0 is 700, 1 is 784. Every year it's like you're timesing it by 1.12. So to get to 3.5, it's like I'm timesing it on this interval, since it's only half an interval, 1.12 to the 1/2. So then you can add all your powers when you're multiplying. So we would get 1.12 to the 3.5. That's how we get that value there. If you wanted to do it a long way, like it was a geometric sequence. All right, so the half-life of an element is 12 years. Find how much of the element remains after 36 years and 30 years when you started with 8,000. So 0 is at 8,000. So every 12 years, so after 12 years, we're down to 4,000, half-life. So it's going to be cut in half. 24 years, we're down to 2,000. 36 years, we're down to 1,000. Okay, so 36 years is 1,000. And then we need 30 years. So 30 is halfway in between here. So every time I times it by 1/2, but to get halfway here, I'm going to times it by 1/2 to the 1/2. Okay, so take that 2,000, times it by 1/2 to the 1/2, because it's half of an interval to get to 30. Okay, so take my 2,000 times 1/2 to the 1/2, and that gives me 30 years equals 1,414.2. Okay. Here's a function, f of h equals 200 times 1/16 to the h. It describes the amount of medicine, f of h, in milligrams in a body, h hours after administering 200 milligrams of medicine. How is the amount of medicine changing every hour? So h is hours, so every hour you only keep 1/16, because you're going to take 200 times 1/16. So I would say 1/16 of the amount at the start of the hour remains. By what factor did the medicine decay in the first 15 minutes? So 15 minutes is 1/4 of an hour. 15 out of 60 is 1/4 an hour. So it's going to be 1/16 to the 1/4. So this is the same thing. By what factor does it decay? So it's still only 30 to 45. It's still 1/4 of an hour. So in that time period, whatever your value was at 30 minutes in, you're going to times it by, to go from here, times it by 1/16 to the 1/4 power, okay? Suppose at some point after taking the medicine, there are 32 milligrams of medicine in the patient's body. How many milligrams are in the body 45 minutes later? So 45 minutes out of 60 is 3/4 of an hour. So basically, it's not a full hour interval. So you're going to take that 32 and you're going to times it by 1/16th to the 3/4, which, what does that give me? Which gives me 4. Okay. So our goal, I can explain why an exponential function changes by the same value over equal intervals, even when those intervals are not whole numbers. So you just got to figure out what you're dividing the interval by and then take it to that power 1 over that number. All right, so last one here. Between 1998 and 2008, inflation for prices of goods and services has been about 51%. So every 20 years, you times it by 1.51 because you're increasing by 51%. So I'm going to maybe write that down. Every 20 years, we multiply by 1.51. Suppose a salon charged $18 for basic haircut in 1998, has been raising prices by a steady percentage each year to keep up with inflation. What is the price of haircut at the salon in 2008? So we started out at 18. 2008 is 10 years out of the 20. So you're going to times that by 1.51 to the, really, you could say 10 out of 20, or you could just say, it's 10 out of 20 is obviously 1/2. So I'm going to take that to the 1/2 power. So that gives me 18 times 1.51 to the 1/2, and that gives me 22 point, I'll round to 2 decimals because it's money, $22.12. In 2003, the salon charged $19.95 for a basic haircut. Find the cost of the basic haircut in 2013. So it's 10 years from then. So again, it's half of a 20-year period. So it was $19.95 in 2003. So from 2003 to 2013, it's 10 years. So this is times 1.51 is every 20 years. So it's 10 out of 20. So again, just like I did over here, I'm going to get to the 1/2 power. So 19.95 times 1.51 to the 1/2 power, I get 24.15. Okay. So thanks for watching. I hope you enjoyed this video, and we'll see you next time.